In this video, we want to talk about how to use the Squeeze theorem to find a limit. So first, we want to talk about what is the Squeeze theorem. So let's take a look. What do we mean, Squeeze theorem? Okay, so if you have three functions h, f, and g, so satisfy this condition. Hx is less than equal to fx, less than equal to gx for all x in an open interval containing c, except possibly at c itself. What does that mean? All those going to hold for any x, but at c, that inequality may not be true, because and at c, the function may not be defined there. Okay. And if the hx, which is this function's limit exists, and this function limit exists, and they are equal, then this function limit also exists and equal to the same limit of f and h and g. To describe this theorem, we use this graph to take a look here. So you have this gx. You can see the gx is above the fx, which is bigger than fx, and fx is above hx. So hx is the smallest function. Okay, the gx is the largest function. Fx is between. So fx is between. So that's just like a sandwich here. Okay, that's the reason sometimes we also call that theorem the sandwich theorem. Okay, so now what do we do here? You can see when x approaches to the number c here, and what happened there is this gx, the limit exists, which is L. The hx limit also equal to L. So because fx is between the gx and the hx, so that tells us that fx cannot go anywhere but between the limit of gx and hx. So since the limit of gx and hx same, so that means that force the fx's limit must be same as the fx and gx's limit. So in other words, algebraically, so here if the hx and gx exists, here what we have here, we can say limit x approaches c hx and is less than equal to limit x go to c fx less than equal to x go to c and gx. Because this limit exists, according to what we did earlier. In function, the limit preserved the inequality, which means if that's greater than equal to, after you take a limit, it's still going to be greater than equal to. Their limit satisfy the same condition, same inequality. So what we have here now, if we know this limit is L, this limit is L, so you can see you're going to have limit x go to c fx greater than equal to L, less than equal to L. But you notice L and L, that's the same L. Between these two, which means the same, you can't have something different than this L, because there's nothing between the two L. There's nothing there. So, but this thing must be equal to L. Okay, that's the Squeeze theorem. Okay, that's Squeeze theorem. So, from the Squeeze theorem, many times, okay, when we use Squeeze theorem to find a limit, say like this case, and if we know the limit of h, we know the limit of g. If the fx, we even do not know the function fx looks like, but if it satisfies this condition, we know this limit of f, okay, must exist and equals their limit. So here, this is one of the example here. use the squeeze theorem to find limit as x approaches c there. Okay, so if you sketch the graph of 4 minus x squared, okay, 4 minus x squared. So what do you have here? You will find this graph looks like this here. This is a quadratic function. So this is -2, this is +2. And 4 plus x squared and looks like this here. Okay, that's quadratic. So fx is between these two graphs. That means fx is something like this here. Okay, and so what we have here, you can see that's definitely satisfies the so-called squeeze theorem. And fx is between the two functions. And so if we can find the limit of this and the limit of this as x approaches c, which is 0, and so hopefully and the squeeze theorem can be applied there. Okay, so what we have here, we go ahead and take limit x approach 0 for this because c equal to 0. So 4 minus x squared equal to 4. Okay, you just simply substitute x equal to 0 in there. And also you find x goes to 0 and 4 plus x squared and equal to 4 too. So now, because that's two functions and satisfy the squeeze theorem, and their limit actually same. Okay, so by the squeeze theorem, you notice here we don't know the fx looks like. We just know the fx is in between these two functions. Okay, so that tells us the limit x goes to 0, fx must be same as these two limits, which is 4. So that's it. But this is for a function we do not know. But when you have this, this is quite easy to realize. You have to use the squeeze theorem. Use the squeeze theorem. But at certain times you have a problem. You may not realize you have to use the squeeze theorem. So let's take a look at the next few examples here. We want to take a look at the first example. Okay, we want to find the limit of this. X squared times sine 1 over x. And first, and according to the strategy of the limit, when we try to find limit, first we try to say, go ahead and do substitution. But that's the case you can't. When you do substitution, this is 0. This is 0. But the sine 1 over x, this thing here is undefined. But you can't say, oh, this thing is 0, that's undefined. I'm still going to get 0 there. It could be 0, but it could be something else. But we're not sure there. So how am I going to find this limit? So here, this is how we're going to find a limit by using squeeze theorem to find the limit of this problem. Okay. So first, here we have a sine 1 over x. Because we know sine function is, it doesn't matter this argument looks like, but that's functions always between -1 and 1. Okay, from -1 to 1. So which means that's greater than or equal to -1 and less than or equal to 1 for any x. Not equal to 0. Okay, for any x not equal to 0. That's true there. Okay, so now what do we do here? And so we can multiply the x squared to this inequality. Okay, so here we multiply x squared to the inequality. So now it is negative x squared and x squared sine 1 over x squared. Because the x squared is greater than 0. Because what we choose, the x, is definitely not equal to 0. So we multiply x squared. The x squared always positive. When you multiply a positive number to the inequality, you does not change the inequality's direction. So which means you're still going to keep the same direction as what you have before. Okay, so you satisfy that condition. Now it's time to use the squeeze theorem. And because limit x goes to 0, negative x squared, because it's polynomial, so the limit, you just go ahead, do the substitution. So we have that's equal to 0. And similarly for x squared, when you take limit, when x goes to 0, x squared, of course, the limit also equal to 0. So now, because this limit goes to 0, this limit goes to 0, so by the squeeze theorem, this limit must exist, and the limit also equal to 0. Okay, so now we're going to say by the squeeze theorem, okay, limit x go to 0, x squared times sine 1 over x and equal to 0. That's how we need to do. Okay, so make sure you indicate this because you want to make sure that's go to 0, that's go to 0. Force the middle one must go to 0. So that's where then the limit exists. So now we found that limit actually exists equal to 0. Okay. So now, how about this one? When you see that one, you may immediately think, oh, that's 2 must be exactly same. I won't say exactly same, but similar in this case. Similar. So, but it's not exactly same. Let's see how we do this problem. Okay, see what's the difference between this one and this one. Okay, so I do this one. So here I want to find limit x approaches 0, x cosine 1 over x. I want to find what that's limit. Or does that limit actually exist? First, same as what we did like earlier. Because cosine 1 over x, cosine any argument, here the argument does not have to be 1 over x, any argument, cosine function always greater than equals -1, less than equal to 1, from -1 to 1. Of course, here you cannot allow x equal to 0, so you say x not equal to 0. But now you say, oh, then we go ahead and multiply x. No, that's case you can't. Maybe you say, why that's case you can't? Because that's case you multiply x squared, you know x squared is greater than 0. Okay, because x squared is greater than 0. So when you use something greater than 0 to multiply the inequality, it does not change the direction of the inequality. But not for this case. If you multiply x, you do not know that x is a positive or negative. Remember, x approaches 0 means x can approach 0 from left side of the 0, which is negative number, or right side of 0, which is a positive number. So now I have to consider this separately. So here I want to say if x is greater than 0. Okay, so here then I'm going to multiply the x to this inequality. So you get negative x and x cosine 1 over x and x. because this greater than 0 multiplied the inequality, a number is bigger than 0 multiplied the inequality, does not change the direction of the inequality. Okay, that's what we have here. Now we can apply the Squeeze theorem to one side of limit. So because x greater than 0, so you're going to take the limit x goes to from right side of the 0, because greater than 0, right side of 0 we use 0 plus, okay, and negative x equal to 0, also equal to x from right side the 0 to approach x, because that's a polynomial. You can just do substitution. Let's give you 0. Okay, so that by the Squeeze theorem, okay, so here we have limit x approaches 0 from right, x cosine 1 over x equal to 0. That's from right side when x greater than 0. Okay, so here we got this thing here. But how about if x less than 0? If x less than 0, so you will see here, okay, you will see here, and you're going to have, because that's less than 0, you multiply a negative number to both sides, I mean to all this in inequality, you have to change the inequality immediately. Okay, change the direction of inequality immediately because you multiply x less than 0. So you're going to have, okay, negative x greater than equal to x cosine 1 over x greater than equal to x, because you multiply a negative number to this inequality, you change this to this direction. So now you have limit x approach 0 from left side because x less than 0. Negative x equal to 0, and also equal x approach 0 from left, that's x that equal to 0. So now you again you're going to say by the Squeeze theorem we have limit x approach 0 from left, x cosine 1 over x equal to 0. So now we combine these two together. Remember, if a limit exists, means left side limit and right side limit both exist and equal. So now we can conclude with a limit x goes to 0, x cosine 1 over x equal to 0. Okay, so that's how we use the Squeeze theorem to find limit. Many times, something like this can't, you are not sure the function actually looks like, okay, or you are not sure the function value actually, happened to this function value. So you may consider use the Squeeze theorem. Okay, so that's the end of this video.